so we still have 20 minutes. Uh, Donghang is my colleague from TikTok who present this project. I'll give an overview. Donghang, can you share the slides in the meantime?
Sure.
We open source this project. This project called Trustless Attestation Verification. We open source this project last year, end of last year and early this year, and mainly to address the trust boundary of attestation verification service. The method we're using is zero knowledge proof, or purely mathematical um, tool to do the attestation verification. And then when we open source, we a lot of people are interested in this project and also contribute, ask questions in the open source community. But open source, attestation is not simply like comparing the measurements and collateral. So we thought this good to contribute, donate as a CCC project and integrate with a Verison as a whole. So that's why this time we want to reintroduce this project in CCC and seek some feedbacks in probably this and the next two tech meeting, and then we decide whether to accept this project as a CCC project. Yeah, Donghong can share the slides.
Yeah. Can you hear me well?
Yeah, please go ahead, Donghong.
Yeah. Thanks, everyone. Sorry, I have to restart Zoom so that I can have the permission to share my screen. So yeah, thanks, Vincent, for the introduction. And our project is called Trustless Attestation Verification. And today I'm going to talk about the idea behind and what's our open source status right now and our future plan. So this project is currently open sourced in GitHub under TikTok Privacy Innovation. And yeah, we can start here. Let's first talk about the scenario of this project. Now we are considering a redemption party using a TE in cloud service. So basically, you can think of this as the Google Cloud, and the redemption party wants just to use their TE nodes. And the first question for the redemption party is of course that this cloud environment has basically very limited or even no visibility to the redemption party. Redemption party does not know what's happening inside. And the first question is natively, do I really interact with a TE node or not? What if this cloud service is malicious and just provide normal machine? Then the moment that I send the data to this cloud environment, the privacy of my data got immediately lost. And thankfully, we already have solution for this. The attestation can enable the TEs to prove themselves. And since this is the Confidential Computing Consortium meeting, I will not just introduce this in detail. So the attestation procedure usually check several things. For example, it can check the certificate chain of the certificate. It will check whether the report is properly signed. It will also check some vital properties of the TE nodes, such as the firmware version and microcode version. So if everything's good, the redemption party now can be confident that I'm actually interacting with a legit and security environment. And in the cloud setting, there are several ways to do attestation. The first one is obviously the TE node can directly send the attestation evidence directly to the redemption party. So this is more like a peer-to-peer way. However, in the cloud setting, especially in reality, people prefer a kind of another architecture. So here, there will be a attestation verification service. And for the rest of this talk, we will call it AVS. So this service is usually hosted by the cloud service provider. So now instead of allowing TE to directly send the attestation evidence to the redemption party, instead, now TE can send evidence to the AVS. So AVS can verify the attestation report on behalf of the redemption party. And if everything, and simply just sends the attestation result back to the redemption party. So there are a lot of advantages. For example, now it's easier for the cloud service provider to manage reference values. Rely on party does not need to track all those values. And also the remote service attestation service now can be easier to integrate with other cloud functionalities such as authentication and token issuing. And it's also good for the rely on party because rely on party does not need to know how to verify the attestation evidence. So its computation burden is also eased. However, this structure, although with all these advantages, it also brings problems because now the attestation verification service has to be trusted. So in ideal world, when we use the TE nodes, so we want to only trust the TE node itself. So that's the ideal world on the right-hand side. However, right now in practice, on the left-hand side, we now have to trust both the TE and the AVS. And since the attestation verification service is usually hosted by the cloud service provider, so now it also means sometimes we must trust the cloud service provider as well. So although the cloud service provider are trustworthy most of the time, but there are still some corner cases that might happen. For example, what if the attestation verification service becomes malfunctioning or buggy after some version update? Or what if now the attacker wants to launch attack on this system, since the security of the system depends on its weakest part. Although the TE environment is secure enough, but now the attacker can just choose to attack the attestation verification system. So in general, it's like the larger trust boundary means larger risks. And so the next question is natively, can we make the AVS trustless? So what if the attestation verification service can prove to the relying party that it is following the correct attestation logic, which means it is being honest? And this can actually be solved by cryptographic proof. So now we can say instead of trusting this service, you can actually just trust math. And the crypto tools we use here is called zero knowledge proof, and it's basically a two-party cryptographic protocol. It can allow one party to prove to the another party that the statement is true without revealing any additional information. For example, that you can prove that you are a citizen of a country without even giving your name or your passport, let's say. Or you can prove that your age is over 18 without disclosing your actual age or your ID card. So this concept actually is much more popular in the community of blockchain. And with years of development, the zero knowledge proof becomes very efficient to prove very large scale of computations. Specifically in blockchain, actually the zero knowledge proof is used to prove the correctness of the computation. For example, in Ethereum, people use it to verify the off-chain computations. And in our scenario, actually, it's very similar. What we want to prove is that the attestation verification service is actually running the attestation logic correctly. So it's also correctness of the computation. And there are several variants in the zero knowledge proof family that are very good in our use cases. For example, one of them is called ZK Snark. It has several properties such as the proof verification could be very fast and the proof size is constant. So in our scenario, this means the computation burden and the communication burden for the relay party will be very small. So it's more kind of user-friendly. That's the good part we want. And our solution here is we want to embed zero knowledge proof into the attestation verification. So now the attestation verification service need to generate a zero knowledge proof so that anyone can verify that the attestation service actually is running the expected attestation logic. So next is the basic flow of this system. So we will have a setup phase. It can be either trusted or not trusted, depends on what kind of zero knowledge protocol you are using. But the general idea is here, you will have, first you will have a attestation verification implementation. You can put it online and everyone can audit, endorse, or challenge it if they find something is wrong. So after this phase, we will have an agreement of a version of attestation verification implementation so that everyone think it is good. So this can be put online so that everyone can check. And next step is actually during the attestation verification, when TE sends the attestation evidence to the AVS, AVS will actually generate two outputs. The first one is the attestation result, and the second one is actually a zero knowledge proof. And this proof is used to prove that the code it runs is actually consistent with the open source version that we just built in the trust phase. And now Reliant Party can actually get just check whether this zero knowledge proof is valid. If it is valid, it means the attestation verification service is being honest. So you no longer need to trust it. Now you can only just trust math. And there are also challenges introduced by distributed confidential computing. Let's say we have a TE cloud service that is hosted by a lot of TE nodes, a cluster of TE nodes, let's say maybe 1,000 TE nodes. So in this setting, multiple TE nodes need to collaborate to provide this service. But as a Reliant Party, if he wants to use this service, he needs to ensure that the entire cluster are secure. So in this case, the Reliant Party may have to verify 1,000 attestation evidences. But also the TE themselves, they require mutual attestation before sending private data to other TEs. So these are all the challenges brought by the distributed confidential computing. And our goal here is actually we want to minimize the efforts of both the Reliant Party and the TE nodes. For example, even with the 1,000 TE nodes running to support the service, the ideal case is the Reliant Party can still only verify just one proof, and then it can ensure that the entire cloud is attested properly. And this actually can be done by a concept called proof aggregation in zero knowledge proof. So in this figure, you can think of every single proof at the bottom is a attestation proof for one single TE node. And the proof aggregation for ZKP can allow you to aggregate proofs layer by layer to form this kind of a tree structure. So we will have a one proof at the top. And the idea is the final proof, the proof on the top is valid if and only if all single proofs at the bottom are valid. So this basically is like now you only need to verify the proof on the top, and you can be sure that all the attestations for each TE is done correctly. So now the proof aggregation in distributed TE system can be much easier, since in cloud service, we can always find a role of orchestrator. This could be load balancer or gateway. So there's always a role that you can you can grab all the attestation proofs together and aggregate them. So now the orchestrator can just do the proof aggregation and send one single proof to the Reliant Party. And this single proof shows the honesty of the entire cluster of TEs. Also, mutual attestation becomes easier because previously the TEs might have to attest each other. So this is more like a peer-to-peer network. But now each TE can just send their attestation evidence to the orchestrator. Orchestrator will do the proof aggregation and send the aggregated proofs back to the TE. So this is essentially we are changing a peer-to-peer network into a star network to reduce the communication cost. So this is basically the idea we have as of now. And after we tested, we find the performance of the zero knowledge proof sometimes may not meet your requirement. For example, if the proof generation is kind of slow and takes several minutes, but you are targeting at starting up a TE environment in seconds, so there might be a performance gap. So we have a alternative setup here. So generally you can use our project, the Trustless attestation verification, as the root of trust. And we can use that to bootstrap one single TE. And this single T, inside this single T, we can run a general attestation verification service such as Verizon. And this attestation verification service can be responsible for all the attestations for the rest of TE. So in this way, you can see there is still, you still don't need to trust like any party in this whole chain, because the root of trust actually is built on the zero knowledge proof. So this still, you don't need to trust anyone in this system. And as for the open source status, our plan is we want to implement this idea with various zero knowledge proof backends because they have different trade-offs. And as of now, we chose two backends. The first one is called Circum. So it's kind of like a circuit-based ZKP backend. So you need to write your computation logic in terms of a circuit. And the good part here is it has very transparent trusted setup. So you can use that to build trust. For example, the Confidential Computing Consortium could be responsible for the trusted setup. Everyone who wants to participate can join this trusted setup to make sure the general trust is built. Also, it has very clear security model, but the bad part is that it is kind of slow. In our experiments, it may take like 10, 20, 30 minutes to generate a proof. And the second backend we choose is called Risk Zero. It's kind of more of like a virtual machine-based zero knowledge backend. So the good part is now you can implement your attestation logic in Rust. So it's easy to implement, and also it's easy to audit, since if you audit the circuit, it's going to be a headache, especially for the large scale circuit. And the good part for the risk zero is it's very fast. If you in our benchmark, the best we can do is we can finish the proof generation in 10 seconds. And the bad part is has slightly more complicated security model, but it's still good. It's still verified. And now we have already open sourced two repositories on GitHub. The first one is called Trustless Attestation Verification. This is kind of serve as our main entry. It does not have any implementation inside, just introduce our ideas. And the second repo is our implementation in Circum. So this is already open sourced. So in this Circum implementation, we use gross 16 proof, which is the ZK snark. As I mentioned, it has a constant proof size and very fast verification. So it's more user-friendly. And we do it for the AMD SEV SMP attestation verification as of now. Also, we provide a user-friendly command line interface based on Makefile. So as of now, we already got support from the community. We connect with multiple ZKP companies. And also we already see independent community contributors. They opened 20 plus issues and submit 6 pull requests. These are not big achievements, but I think it's a good start since we are still early on this. And also, meanwhile, we are also testing the deployment of this idea in our internal use cases as well. So as for the general timeline, we will open source the Risk Zero version in this month. And we have several things in agenda for the future plan. For example, we want to provide a example code for the integration demo that so that's basically the implementation of this idea, so that we want to use our project bootstrapped a TE to do the general attestation. So this is the first plan. We also have the second plan is we want to do a demo for the proof aggregation. So it's basically this idea. So we want to try to use one single proof to attest the entire cluster of TEs. And finally, we want to support some more TEs, since right now we only have attestation logic implemented for MD, SEV, SMP, and in the future we plan to support more. That's the general timeline. So this basically the future plan. The timeline might not be exact accurate like for each queue, but that's the thing we have in mind. Yeah, that's basically everything I have today. Now,
Thank you for that. Do we have time for a question from you? from Fritz rather for you.
So quick question on, maybe you said it at the beginning and I missed it, but can you say why you actually chose zero knowledge proof? So maybe if you go back to your architecture drawing you had in one of the earlier slides, it always depends on the properties that you want to have, right? But what does zero knowledge give you? What properties that you wouldn't get by, I don't know, normal TVM? Because aggregation you can always do with a normal TVM and things like that. So why in your system you want the properties of zero knowledge?
So that's a very good question. So here, actually, the property that we want is just a cryptographic proof. And here, the zero knowledge proof, the zero knowledge property actually is not used, since by default, the whole attestation procedure should be transparent, which means you should not hide anything in the attestation logic. So in this sense, what we need here is a cryptographic proof. It can be with zero knowledge property or without zero knowledge property. But after we dig into this field, after checking what are available, we find that the zero knowledge proof families are actually the most efficient, and mainly thanks to the contributions of blockchain communities. So even in terms of the efficiency, they are faster. So that's why we choose zero knowledge proofs. But you are right that the zero knowledge property is not required in this scenario.
But attestation also have cryptographic statement of the relying party, right? So why cryptographic proof? I don't get that part.
So for the cryptographic proof is more of like a proof of computation. We want the attestation verification service to prove that it's running the correct version of the code.
But you don't want to use CC for that.
Right, because this is kind of, the idea of this project, we want to bootstrap the trust for the CC. Since this is a attestation, before the attestation, you have no party to trust. And here,
okay.
Yeah.
Sure enough, yeah. So sorry, Alec, go ahead. Maybe you can squeeze in.
I think I just had the follow-up question for your question, maybe just taking it up a level, which is to say this attestation aggregator that you're proposing, it's not part of the TCB. Am I right about that?
Right, it's not part of TCB. It's more kind of like an attestation verification service.
Right, it's not part of the TCB, and you don't have to run it in confidential computing because of the beauty of zero knowledge proofs. I get it now. Okay, cool, thank you.
Yeah,
and I think that's the question Fritz asked as well, but he asked it at too low a layer for me to understand it.
Yeah, that's correct.
I'm sorry, I just want to add on the zero knowledge part. The zero knowledge part we are discussing internally for the attestation itself. Currently, all is transparent. But if you think about the software attestation, some of the property you want to hide, but you want to prove to the relying party. I can, for example, the network topology in the cloud setup. You want to prove that it follow a certain pattern, but you don't want to reveal all the details of the network topology or software configuration. Then you can use zero knowledge proof without revealing the detail, but can prove some of the property inside the cloud.
Well, thank you for the presentation today. Obviously, a little bit more that a little too much to squeeze into one meeting today, but I'm glad that we got through this. I hope people take questions now to the TAC mail list or to the TAC Slack. I know Mingshen is on both. I don't know if Lu Donghang is on either of those, but I imagine Mingshen can facilitate.
Yes, of course. And I think we can have another Q&A session in the next tech meeting and also discuss the donation thing.
Okay.
Thanks,
well, with
Mingshen.
that,
Thanks, everyone.
thank you, everybody.
Thanks,
Thank you.